MetroVista Mall recently upgraded to a smart parking system. It worked perfectly during normal days. However, during a holiday peak season, the system completely crashed. This happened because over 2,000 cars tried to enter the mall at the same time. Our analysis shows that the problem was not because the hardware, but because the operating system itself could not manage its resources properly. So we found four main OS problems. First is inefficient CPU scheduling because too many big tasks run at the same time. This causes high context switching, meaning the CPU spend too much time switching between tasks until it froze. Second, race condition. Multiple system parts try to update the database at the exact same time without any control. Because of this, data got corrupted. The outside display would show available, even though the parking was already full. The third is memory overload. There was no limit on memory usage. Some apps took up too much RAM, which stuffed the CCTV system and made the live video freeze. The fourth is slow response. The system just could not handle the massive workload in a short time. Because of this issue, our group is acting as OS consultants. We have three clear objectives. First is to diagnose. We want to find the exact bottlenecks in the OS kernels that cause the crash. Second, to evaluate. We will look at how the current system schedules, processes, and handles threats. Third, to remedy. We want to propose real OS solutions like using multi-text logs, optimizing CPU scheduling, and switching to a better multi-threading model to fix the system. Now, let's look at how the system works and how it uses OS resources. If you look at the diagram, a car enters the mall, the ANPR camera scans the plate number, and the database scripts log. Then, parking sensors track empty slots and update the digital ports and mobile app. Finally, the driver pays at the kiosk and exits. The biggest challenge for the OS is that every part of the system wants different types of resources. As you can see, the NPR camera are compute bound, meaning they need a lot of CPU power to process images. The parking sensor are I/O bound, which means they generate a lot of network interrupts. The database is disk I/O bound, requiring memory locks to keep data safe. And the CCTV system is memory bound, needing a lot of RAM for video streams. When all these different demands hit the system at the same time during peak hour, the OS got overwhelmed and crashed.
Okay, next we will go to the operating system concepts that apply in this system. First, in process management, the operating system handles many independent processes at the same time. In the smart parking system, it manages vehicle plate recognition, parking sensors, payment kiosks, CCTV monitoring, mobile applications, and cloud synchronization. The OS coordinates all these processes to make sure the parking system runs smoothly. Next is thread. Each application can perform multiple tasks at the same time using threads. For example, the CCTV system can process multiple camera feeds simultaneously, while the mobile app can handle user requests, check parking availability, and communicate with the cloud server at the same time. This allows real-time performance. For CPU scheduling, the operating system divides CPU time among all active processes. This ensures that every part of the system gets enough processing power. In this case, parking sensors, payment systems, CCTV, and mobile services can all operate without delay or interruption. In process synchronization, the OS ensures that all processes share data correctly. For example, parking sensors, digital displays, and mobile application all access the same parking database. the OS makes sure the information is always consistent and not corrupted. For memory management, the operating system allocates memory to different applications efficiently. It ensures that each process like CCTV, payment kiosks, sensors, and cloud services get enough memory to run properly without interfering with each other. And finally, multitasking allows the system to run multiple applications at the same time by quickly switching CPU tasks. This gives users the impression that everything is running simultaneously, such as entering the gate, checking parking availability, making payments, and being monitored by CCTV all at once. Next, we go to the problem identification and analysis. Actually, this system is okay in normal condition, but the problems start in peak hours or event. During the mega sale event, more than 2,000 vehicles entered the mall within a short time. The system had to process a large number of requests simultaneously, causing CPU usage to become very high. As a result, the system becomes slower in responding. Processor become overload. At the entrance, customer experience long waiting times because some automated barrier gates respond slowly or stop working temporarily. This led to long queues and traffic congestion outside the mall. Next, the digital displays sometimes show available parking spaces even when the parking area was already full. This caused drivers to keep searching for empty spots, increasing congestion inside the parking area. After that, some automated payment kiosks became unresponsive during transaction. In some cases, customers were charged twice or unable to complete payments. There were also missing transaction records in the database. Next, the CCTV system became slower during peak hours. Live video feeds were delayed and security alerts were not received on time. Because of this, a minor accident inside the parking area was not detected immediately. This happened because video processing requires continuous CPU and memory resources, which became limited during high system usage. Overall, the system performance dropped significantly when all applications ran at the same time. Services become slower and less stable. The IT department later found that the hardware was not the issue. The main problem was the operating system could not efficiently manage CPU scheduling, memory allocation, resource sharing, multitasking, and synchronization under heavy workload, which affected the entire system stability.
Next is the current process running in the smart parking system. So firstly, we are going to go through the current workflow of the system. First, when a vehicle enters the parking spot, the camera will detect the vehicle and capture its information. Then, the sensor will activate to check whether the parking spot is occupied or not. After that, the database will update that information whether the parking spot is occupied or not on the mobile app. After that, the information will be displayed on the mobile app board. Then we are going to see the current limitation of the system. So firstly, the system use high memory usage, resulting in laggy system. After that, slow inter-process communication that can happen during peak hour, and it will cause delay or misinformation among the system. After that, high context switching overhead, and lastly, slower real-time response during peak hour, resulting in conflict on the status of the parking spot, whether it is occupied or not. Based on this analysis, we would like to recommend for the system to implement multi-threading architecture, where instead of creating separate heavy processes, the smart parking system should use one main process with multiple threads such as camera threads, sensor thread, database thread and notification thread. And there are several advantages for using multi-threading. First, multiple tasks can be executed simultaneously without delay. Second, the system responds faster when vehicle enter or leaving the parking area using multi-threading. Third, memory consumption is lower because threads share the same resources. And lastly, the context switching between threads is faster than before. Next, we are going to go through the existing scheduling limitation. Currently, the smart parking system faces several scheduling bottlenecks, such as camera processing, sensor monitoring, database update, and user interface update, all compete for the same CPU time. So, during peak hour, this competition might cause delays in updating parking information. As a result, user may receive outdated parking information, thus creating conflict on the parking spot and lower the user satisfaction on the system. Next, we are going to look at the scheduling problems that are identified in the smart parking system. Firstly, lack of priority control, where all tasks are treated equally even though some tasks are more important than others. Second, CPU utilization is inefficient because some tasks consume more processing time while others will remain unchanged. Thirdly, high context switching that can reduce the system performance. And lastly, failure to make real-time execution resulting incorrect parking information and delayed vehicle detection. Next is the scheduling recommendation that we would like to suggest to the system so that they can use it to improve their performance. So firstly, priority-based scheduling, where the system will assign priority levels to each task based on its importance. This approach ensures the most critical tasks are executed first rather than the lesser important tasks. Next, multi-threading with proactive scheduling, where the operating system gains capability to perform dynamic task switching, which allow the scheduler to interrupt a low priority process instantly during time critical event. Thirdly, round robin. The system can implement round robin scheduling scheme specifically for UI component to avoid UI using excessive amount of system resources. And lastly, real-time policies. This is to ensure strict arrival time deadlines for camera and sensor threads.
So my part is all about synchronization, and to start off, let's define the word itself first. Synchronization is an instance of several different actions happening at the same time, or it can also mean two identical actions happening at the same time as well. And when it comes to operating systems, synchronization in operating systems is how the operating system manages multi-thread and makes sure that threads do not access the same resources at the same time. And the same resource that we're talking about in our example is the database. So the synchronization is responsible for the management of loads within a limited resource. So shared resource is a parking database, as I already mentioned, and in our example, many parts of the system use the database at the same time. To name some of them: parking sensors, mobile application, barrier gate, payment kiosk, CCTV system, and cloud servers. Now, what kind of problem does it solve? So when it comes to assigning data to our database, there are a lot of examples of two instances happening at the same time and uploading the data at the same time, which may clash, and as a result make a lot of it will have a lot of consequences. Let me go more in detail about the problem. So the issues are caused when multiple threads attempt to access the same parking database simultaneously. Example of this problem is when, let's say, there is a parking slot A and then it's empty, and at the exact moment one of the threads, the parking sensor thread, shows that slot A is empty, which is correct, but the mobile application thread 2 shows that someone reserved slot A, so it sends a notification to the driver that slot A is actually not free, not available. And then we have also digital display thread 3 that reads old data, and due to it reading old data, and the reason why it happens is because synchronization is not applied in the database, so the database may end up saying that slot A is available even though somebody is already parked there, and this explains why drivers can see incorrect information when they are trying to park. We also have another problem that's called race condition. This basically speaks for itself. It's in the name of the condition, and the reason why it's called race is because two threads race each other in updating the data. So since they're racing, only the fastest one can upload it before the slower one, and because of that the fastest has advantage, and the authenticity of the information then in this case relies on the speed of the faster thread, which is not ideal, because if, let's say, the misinformation is faster than actual correct information, this may create a situation where let's say we have like sensor A and sensor B, and one of them says empty, one of them says occupied. If driver is searching for a space and sensor A is faster than sensor B, so it says that the slot is actually empty, but the sensor B was the more correct information, which says it's occupied, the driver will only read the notification that says that sensor A is actually empty, and it goes on searching for free space, but they never find the space because it actually doesn't exist. And the reason why it happens is because, again, of the race condition, which is when two threads race each other and only the faster one shows the information first, completely removing the information that is brought up by the slower thread. Now, what are the consequences of synchronization, not having synchronization? And to name some, most of the common consequences caused by these problems, for example, wrong parking availability displayed, which I already brought up some examples of why it happens, and the driver searching for spaces that are not even present in the system, which I brought up an example of for as well. Increased chances of traffic congestion. So if a lot of drivers, they keep getting false information, false flag, and they all end up in the same parking space, it will create a really huge traffic of many cars that don't have any space for them to spare, and inconsistency of database records. Yeah, this not having synchronization can mess up with the database records as well, and the payment records may disappear. I'll give an example of this one later on. Occurrence of double charging. This is related to payment. Yeah, let's talk about the payment and how it happens because of not having synchronization in our database. So basically, customer presses a pay button, but the payment thread starts, but suddenly the kiosk freezes, which leads to customer repeating their action. So they have to press the pay button again. After they press the pay button, so this will create two threads that both charge 10 ringgit, and because of that they may get double charged. And the reason why it's bad is because a lot of customers, if it happens very often and if we don't apply synchronization in our system to prevent it, a lot of customers will lose respect and the system will lose its reliability. Yeah. And how can we actually solve this using synchronization method? There are a lot of ways we can go. In our example, in our article, I mentioned reentrant lock, semaphore, synchronized method, and synchronized block. And these are 4 methods that I mentioned in my article that can solve this problem that happens due to not having synchronization. And another example is reader-writer lock. So let's go through one of them, and let's talk about reader-writer lock. This one's focused on who uses the database. Some applications only read, such as mobile application, digital display, and analytics dashboard. These applications only ask the number of spaces and do not practically change anything, while other applications write, such as parking sensors, payment kiosks, and barrier gates. These modify the database. If every reader waited behind every writer, the system will become really slow. So because of that, we can apply this synchronization method, which will help us make it faster. And the way how it works is, since they are only reading information, so let's say the users are only reading information, they can read as much as they want, but whenever we have to apply some changes, the system temporarily removes the access to read from the users and gives us the time to edit our database. And in this case, how is it helpful? It's helpful because now we can change the database before users can see the changes. It doesn't happen at the same time. Yeah, that's all for the synchronization. So now let's talk about memory management. The smart parking management system experienced memory management issue because several applications, including CCTV monitoring, vehicle plate recognition, parking sensors, payment kiosks, and cloud synchronization and mobile services, were running simultaneously during peak shopping periods. And due to them running at the same time at the peak shopping periods, they obviously need a lot of resources, and one of the resources that they were using is RAM. So as the memory usage increased, the operating system struggled to allocate sufficient RAM to every process, and causing slower system performance and application instability. So not having enough RAM may really slow down our system and affect the experience of a lot of our users. And when physical memory became insufficient, the operating system relied more heavily on virtual memory, which is RAM, which increased disk access and reduced overall responsiveness. Inefficient memory allocation also affected multitasking performance and delayed critical services such as payment processing and CCTV monitoring. And because of all of these issues, Memory management helps us solve all of them. And how does it help us? So to improve performance, the system should implement efficient paging techniques to load only the required portions of applications into memory. Use memory protection to isolate processes and prevent data corruption, and apply memory sharing for common resources used by multiple applications. These improvements would reduce memory overhead, improve application stability, and ensure faster response timing during periods of high traffic.
We propose 5 key solutions to address the system resource management issue. First is hybrid CPU scheduling. Prioritize critical tasks like NPR and payment for immediate processing, while round robin is used for less critical tasks like analytic and UI to ensure the fairness. Second is multi-threading. With a thread pool, limit active threads and improve the efficiency since thread can share memory. And third is synchronization methods such as mutex logs, semaphores, and reader-writer logs protect shared data and prevent conflicts. And fourth, memory techniques like paging, segmentation, and LRU will optimize the RAM usage. And lastly, dynamic allocation and cloud load balancing distribute the workload to prevent any bottlenecks. For technical justification, hybrid scheduling ensures time-critical tasks like payment processing are completed without delay, while lower priority tasks still get fair CPU access to prevent starvation and reduce idle time. For multi-threading, multi-thread with a thread pool improves communication via shared memory and reduce the context switching overhead while increasing the CPU utilization. Mutex logs ensures only one thread update at the parking database at a time to maintain data integrity, while semaphores control access to share resources like sensors to prevent overloaded. Reader-writer logs allow many users to check parking availability at once, but restrict writing to one thread, and reentrance log allows safe repeated access by the same threads and preventing the deadlocks. For memory management, paging ensures only essential program paths are loaded into RAM to reduce memory usage, while segmentation organizes memory logically to improve process handling. Memory sharing reduces duplication by allowing multiple processes to use the same resources. And then the LRU patch replacement algorithm reduces this access and sweeping, keeping critical process in memory and preventing slowdown. For resource allocation, dynamic priority-based distribution ensures vital service get sufficient resource, while cloud-based load balancing spread workload evenly to avoid any bottlenecks and crash during peak demand. As a result, CPU efficiency increased by 85% and response time improved by 80% with improvement system stability and data accuracy. In conclusion, the smart parking management system failed is not due to the hardware limitations, but due to weak operating system resource management under high traffic conditions. So the key issues including the poor CPU scheduling, weak synchronization, inefficient memory management, and limited multitasking. To solve this, we propose hybrid CPU scheduling, multi-threading with thread pools, strong synchronization methods, better memory management, and dynamic load balancing. These improvements makes the system more scalable, reliable, and responsive during peak hours by ensuring accurate real-time processing and better resource use. This also improves user satisfaction, reduces congestion, and ensures the long-term system sustainability. So that's all from us. Thank you.